Thank you so much. Welcome. I'll try to tell you something about using Python in scientific problems by not a programmer, but someone who has to spend a lot of time on understanding the physics and using Python as a tool. And you'll see that the biggest requirement is someone who can help us to better use Python and better use tool for solving problems. I will tell you something about the problem just to give you the idea of what we are doing, and then I'll tell you a moment about the experiments and some of the things that we did. It won't be maths or too much physics, I'll promise. But this is just to tell you that we are trying to prepare the next generation of devices that people will use in the future. In particular, we are trying to understand if it's possible to have different type of memory. Usually we have memory in hard disk where something is moving, and so you can read the information. The idea now is to have, let me see, this type of device. Okay. You see here, blue and red means information, 0 and 1. In physics means magnetization, can be up and down or left to right. What you do is you apply a current to this track you see here. You apply the current and you move this guy here, you see, which are called domain walls. These are the domains. They are moving, and you can read them here. So you store information, but you don't move anything except the information itself. This seems to be a very fast way, a very fast reading and writing device. The problem is that we still don't know how to do it because there are big technical problems. Okay? But this is the idea of the future. And also, it's also interesting because it's possible to do also the logic with domain walls. Domain walls are these interfaces between 0 and 1s, okay? Just to understand. So there is a sort of, the community, scientific community in magnetism is very happy to work on this type of new devices because they seem to be the next generation of devices. Well, forget all the details, just look at the pictures because it can be the interesting part. And here you see that we would like to understand the motion of these domain walls, these interfaces. What you see here are the position of interfaces, let's suppose this red one, at a certain moment. When the system evolves, it moves from red to green or blue, and so you see that these interfaces moves. And there is a lot of physics to understand behind this, because what we call events are motions of these interfaces, for instance, from red to yellow, which goes not smoothly, but in steps. So there are jumps. This interface moves jerky from one position to another. And if you do the statistics, you can see they have very simple, for us, but believe me, they are simple, let's say, distributions which typically have numbers associated. And this number changes, and people are puzzled by this number evolving in some way. So I don't want to enter too much, but understand how these interfaces evolves in time and in different situations, it's a very important problem to solve, because the point is understand the dynamics, as you see in the devices at the beginning. It's fundamental for a real application. So my work of the last 2 or 3 years was to try to detect this. Oh, can we switch these slides? Because I'm going to show you a movie, and I don't know if it's clear enough. It's quite. I'll try to. Okay, excellent. So what's happened? At the beginning, you don't have anything, or you have everything, let's say, black. And then you start having these fingers entering your system. These are actually these interfaces, which are not very simple, like in the device I show you. So they are not straight. They make these very strange patterns. And you see the sequence. So you see they are disappearing completely. Let me see if I can start it again. And every time you see there are jumps, there are changes in the monetization. What you see by white and black are monetization in one direction and in the other direction. So my goal is to try to understand and to determine these steps, these changes. Okay, this is the final result. Probably it doesn't mean too much to you, but you see, it's just to give you an idea of the complexity of the problem. These are all the jumps, all the steps in monetization that one can get. You see, they are very rough, they are very, say, complex. This is the same representation in terms of colors, starting from red to blue, evolving over time. So the same sequence that you saw before was exactly generating this picture. But to get the result, I work hard because I had no clue to get this analysis done properly. I will show you why. But before that, because Valerio, 2 days before, suggested that to switch to Python 3, I said, am I ready? Am I ready to Python 3? So looking at the tool that I use, the first 3 are okay. I don't know about this. I still use Peel, which is probably too old. But I think I can switch, and I will. I don't know. Do you know Maotas? Okay. And also PyTables. PyTables, I think, is very common. And PyTables, I have no idea. No. I have idea that now is at last ready for Python 3. So probably I can switch. I just use it for, no, I just use it. I use it for storing the images, storing the output of the analysis. So it's very good. So I can move it. Malta it's a fantastic for me tool because it gives me some other tools in computer vision. Actually, it will. I will show in detail why it is important for me. In the definition of the regions I'm considering, I will tell you something. But I don't know if it's ready for Python 3. And I also extensively use CUDA and PyCUDA. I know that there are others tools that I think I will like Numba, etc. And so I have to understand it. I don't know if I'm ready for Python 3. So how did I try to solve the problem? Well, I try different, let's say, well-established tricks and methods, like adaptation. Adaptation is a nightmare. When you have very noisy images, it's impossible to get. I mean, you get many edges, but they are clearly wrong. Other algorithms are very good for some problems, but not for mine. And the point is that I want to be able, I need to be able to detect very small details. I don't know exactly, I can tell exactly how small, because it's difficult, because the images are noisy, but I need to find also some small details. I will be a little bit more clear in a few slides. So I had this idea. My images are very simple in the sense they are 0, 1, black, or different gray levels. So what about if I'm able to find the place where each pixel switch from one color to another, okay? The images are noisy, clearly, but when they switch, they seem to have this step in the color. And so, if I make the simple convolution between this noisy function, noisy data, with a step function, I think I'm able to find the place where the color changes, so where there is these events that I'm looking for. And the idea is to get all the images, make a stack of the images, and for each pixel in the NumPy array I get, the evolution is given by the some position. For instance, this is the 0, 0 pixel. And the stacks, so this zeta axis give me the evolution of the pixel, exactly as is shown here, okay? First help, this process is very slow. Stacking the images and get the NumPy array takes 5, 10 seconds. I can survive, of course, but it's pretty slow. And the good thing is that it's already parallelized as a problem, because each pixel has its own, say, story, and I can easily do a parallel computation. This is why I use PyCUDA. And I can also, say, cut the matrix into parts if I don't have enough memory in my GPUs. But except for that, it takes less than 1 second, 2 seconds, even for very large matrix by 500 by 500 or 1,000 by 1,000. So it works. This is to show you the comparison, if it starts, the comparison between the raw noisy images that I showed you before. Here the contrast is a little bit better. And what I get from my analysis in different colors. I would say this is not bad, but there are problems. So in principle, the method is very cool, but we need to solve other problems. Let me show you one example, so to see if it can be good or not. Everything you see here is done on Python. You understand that I use matplotlib and everything. So that's a sort of say. Good representation of the Python I use. If you see one particular part of a raw image and you see the next one, you see by eye that there is a change, and this is the raw difference. You see that there are parts actually which changes from black to white, and this is what my analysis gives you. So if you see the contours of these guys, you see that they are quite well taken into account. Two problems. What about these guys here? Can you tell me if they are here, so if there are changes, tiny changes here, or not? I can tell. I don't have a method to understand if they are reliable or not. I see that these guys are, let's say, in some ways small but compact. So there are regions where they seem to switch at the same time, which clearly are not visible in these pictures, in the raw pictures. But clearly I need more methods. So I was thinking what he's teaching us about machine learning. Because here the system is pretty clear in the sense that I need to understand if these guys actually, considering all the others around him, are switching or not. And the other problem, this is why I use Maotas, is that I have to decide, I need to decide what we call clusters, in the sense that are parts we are connected and which are switching at the same time. But sometimes maybe you have 2 or 3 pixels which are not switching at the same time, but they are clearly close to the big one. So Maotas is a way to give you the freedom to decide how many pixels you want to consider something attached, even they are not physically attached. While the ShiPy, how is called, the ShiPy label is just for neighbors points. And so I can tell if these red and green are the same avalanche, what we call avalanche, the same event. I can tell. Probably I need to do something more sophisticated in this way. I think I did everything. There is a problem. The biggest problem is that when the change in the color, in the gray level, is not so sharp, I mean, it happens in 2 or 3 steps, in 2 or 3 images. Doing the convolution with the step function can give you an error. And this is probably the reason of these guys here. Probably they are switching not so sharp as I supposed to have. And so this is something that I have to tweak a little bit. And just before leaving my lab last week, no, this week, I had a long discussion with a student who wanted to use this tool for her problem, but we realized that in her case, she had large fluctuations of the color of the image, of the gray level, and sometimes she had a sharp transition. So in this case, it's also a problem, but it's a nice problem to try to solve. So when you have large fluctuation because of the light or because some physical reasons, and sometimes you have the sharp change, just to focus on the sharp and not on the large fluctuations of the gray level. And this can be probably a good thing if we want to use this method for other problems, when you have fluctuations of the light or some other things. So at the moment, I am the only one who is able to use the code. And so in general, this is our problem. When we need to export, to give the community back what we did, it's not so simple for us. It's a problem. So this is one thing is how to simply share what we do. This is especially true for the second problem, I just want to show you quickly. And this is related to the same analysis that we did so far, because At the beginning, I show you these distributions that they have a linear part. And these were analysis made as a group that we know, and we wanted to do the same analysis, and we found that there was let's say, an error in the sense that there was something strange, and they didn't take it into account properly. And I want to show you here. If you have an interface, so a line that is jumping somewhere, and the system is large like that, and you observe the whole system, it's easy to say, oh, the blue is what happened. And if you, for some reasons, and in general the situation is like this, your system is much smaller than the whole system, but you are lucky enough that your jump stays inside your window of observation, nothing happens, in the sense that you are doing a good statistics. You keep all the system, I mean, all the event inside your window, but what happens if your windows are smaller and smaller? You are cutting the events in pieces, because these windows, for instance, just sees the small part and forget the others, which are out of that. What about the distribution? Well, this is the distribution of events. Imagine that this size is just the area of the guys here with different colors. And you'll find again this linear part, which is the fingerprint of this kind of systems. But when you start cutting the systems, just imagine to cut the system with these slides, with these two walls, if you want. And the distribution starts to do weird things. And this, considering all the avalanches, and you see that if you want, for instance, get numbers like the slope of this guy, the red and the black, you see that they are not exactly the same. And these are the numbers that are given in the papers. So, and again, if you just consider events that are not touching any of the edges, you have a different distribution, and so on, touching left and right or touching both edges. You have very weird distributions that we dare to calculate. My theorist friends were able to do all the calculation. Don't read them, it's just to show the complexity of the guy. But these are functions, so they are not so simple. They can be very complicated. But I want just to tell you that there are some parameters like tau, zeta, and some others, which are unknown and have to be found by fitting the data. Some others are known, like W, L are known. So the problem for us was, these are the functions that I saw you before, so the complexity increases a lot. So we had 3 functions, 27 fitting parameters, 24 data sets. Okay, compared to the big data, these are small numbers, but for a fitting, it's a nightmare. We say that when we do a simple fit, we are lost in the space of parameters. So you just start with the wrong parameters and you go somewhere that you can return. So in terms of fitting, this is a huge problem. And but if you are able to find some good, let's say, guessing starting value for all the parameters that you want to try to fit, at the end, you can do it. So you can fit 24 functions at the same time with different types of function, having in common some parameters, and some others are not in common. And so what I show you here are let's say, the simultaneous fitting of all these functions. And so the parameters are the best parameters fitting all the data. This was a very interesting and difficult problem that we solve in this environment that we call sloppy scaling environment. There is a large interest from the statistical mechanics community to have such a tool. But going from the simple code to, let we say, a productive tool is again another nightmare. So I'm trying to understand how to do it because I know that people want to use it and can use it. And but here, this is where Python is extremely useful because it's based on the idea of using the least square minimization, which is well known and very stable, but easily can make a simple connection between a model, so a function that I want to use to fit the data, to the data. But also to build a supermodel which contains all the data and all the function. 2 minutes I need, so much less. And after that, I can minimize all the function at the same time. And this is something that I want to finish by, let's say, in a few months, because I think that it can be useful for many other things. I think that I'm over, and I thank you for your attention.
Okay, so we have time for questions.
Right.
Thank you. So as you already pointed out, there is some problem with the data size, maybe some course of dimensionality. How expensive is for you to collect new data points? So like new images and label them maybe? Is it like an expensive process?
No, it's just a question of people doing it, but it's not a problem. It's not a problem. Well, it's not completely true. To have good statistics, good distribution, you need a lot of data, of course. And the other problem is, once you have the data, you have to collect them, you have to analyze, you have to find all the sizes of these guys, and to make the distribution. This is why I need to use tables, because I need to store everything. And this is very heavy. This is true. So it's, the cost is in terms of coding, of course, but also of the analysis, because you never know exactly how many data you need, how many experiments you have to do. And this is the problem. And at the moment, I'm not happy with the distribution I have. And so this is probably why I don't believe to the results of the other groups, because I know it's so difficult, and they seem to be, probably they are much faster than me. But for sure, in this kind of problems, you need to have a large number of data, of experiments. Before that, I was doing the same experiments using a different system, but in that case, I used to have something like 10 to 5, 10 to 6 events, and I could get a very nice statistics. Here, there are at least 2 order of magnitude smaller. And so it's hard. It's pretty hard, yes.
Okay. Okay, thank you. I have 2 questions. The first one, if you could go back to the slide with the, yeah, this one. I didn't get what exactly P of S is. Could you please?
Yes, this is the, imagine this is the number of S is the event, the size, the area. P is the number, but normalized by the a small, let's say, range of S. So it's a It's an histogram divided by the size of the interval that you want to consider. So, to give you an example, if P of S is this value, consider that you have a range like this. You multiply P by this range. This is the number of events that you have at this size.
Oh, okay.
It's a function, distribution function.
Okay.
It's not an histogram, but a distribution function.
Right. Thank you.
So the integral should be 1. That's the
Right.
idea.
Okay, and the other question is, I was just wondering, what kind of algorithm did you use to feed the data into your very complex equations?
You mean this?
No, when you show the all the, like with tau, you say that you have some variables that are unknown, so you,
Yes.
I guess you,
Yes.
you get to feed
Yes.
them. So
I use the least square function, just that. You know that it's based on the residual, so you have to minimize the residuals.
okay,
The only point is to calculate the residuals, but I make a very huge list of residuals for each pair of the data and fitting function.
okay,
So the point is that having so many different data and function, I have to calculate the residual. So I have a specific class to calculate these, but I have a super class which calculates all the residuals and put them together.
so you try all the possible combination.
Yes.
Okay.
No. Combination in the sense that some data I know that must be fit by some values.
Okay.
Then I try some fitting parameters, and I minimize the residual.
So how do you try those fitting parameters?
That's the problem.
Yeah, that's what I'm asking.
That's the problem. That's the problem. Because, again, you are lost in the space of parameters.
Right.
So, you do by hand. I was discussing with Fabio that I told you yesterday that this is our problem. Because when you have function, the guess is a problem. So if you have a simple tool that we can move the parameters and see immediately if the curve goes more or less over the data, and then we start do the fit, that would be nice, perfect. Right. And I really want to do it because this is what people need.
Okay, thank you.
Any other question? Sorry. Yeah. Thank you.
So if you would have to choose like a list of 2-3 things that is really missing for you, what would you say?
I will tell you one. A good, let's say, user interface. That's the main point. This is where I fail. A good user interface. So something that I can't explain to someone what to do using the code because I do everything on the command line, which is something that only I understand. And after 2 months, I forgot what to do. So I have to start again. I think it's a common. If I had a very good user interface, as you showed, for instance, who was enlightened by that would change. And the feature is important because we can see what we put at the beginning and what we get at the end in a simple interface. And that's the step. Because the mathematical tools are not missing. You can try to use something different instead of PyCUDA, use something else. But I don't think it's a problem. The problem is to give it to someone else and make it use it. That's my...
Any other question? Okay, I have one.
Oh, yeah.
What do you need to share the code and the data the results you got? You said that your code is not publicly available and you didn't share any of the implementation you did.
Mhm.
So why don't you did it, and or in case what you need to share the code?
Yes. The other point is that we are pretty lazy on documentation, as everybody knows. And so the second point is that, yeah, I don't have a nice user interface, but first I need to write, I say, quite a good documentation to make the others happy with the code. Yes, so this is taking time. And this is why I stop. This is my
Okay.
because I know that. And no, there is another thing. In physics and in many problems, you first of all try to solve your own problem. And when you try to generalize, the code from 3 lines becomes 30. And so increases because if you want to consider all the different possibilities, that's a big step because you have to take care of all the variables, that the ranges, the variables of the errors of the user. So this is another step that in some ways is scared because I have a colleague who told me, okay, make it work. Don't try to generalize too much because you can do that. It's not your job. So this is the other thing. So these 3 things are quite. But I know that on the same time, when you share it, this is the way that the others can help you too.
Exactly.
So that's the point.
Yeah,
Yes,
exactly.
I am
So
aware of that.
I think that your last point could be easily handled by sharing
Yes.
to the community. So that's when the community comes into play. So
Yes,
just
of course,
to
of course.
generalize and help to
Yes.
change the code in order to be
Improve it. Yeah.
to improve it, and in order to be useful for any other possible application. Okay.
Okay.
Thank you.
Thank you so much.
Thanks a lot.